Hi, welcome to Qubites, your bite-sized pieces of quantum computing. My name is Rene from Valorem Reply, and today we're going to have a deep dive into quantum hardware development. And for this, I'm very honored to have a special expert guest today, Kayleigh Cassela. Hi, Kayleigh, and welcome to the show. How
Hi,
are you
Renee.
today?
I'm good, thank you. Thanks for having me.
Awesome. So before I start, can you tell us a little bit about yourself and your background as it relates to quantum computing, physics, computer science, and so on?
Sure. So I got my bachelor's at Indiana University, South Bend in 2011. I went on to get a PhD in physics at University of California, Berkeley, and then I did a postdoc afterwards and joined Atom Computing in March of 2020. So I've been working here for almost 2 years, and I'm a senior quantum engineer.
Wow, and like this is a great segue into the first questions because oftentimes in this show we talk a lot about the software stack on quantum computers, right? And like for example, what you can already do with quantum-inspired computing and these kind of things. But today we're going to talk about the hardware, right? And so, but for the whole audience here to be fully inclusive, can you just give us a high-level overview of all the components that are involved in a real physical quantum computer?
Yeah, certainly. I mean, I can try. So I like to think of it in kind of a few different areas. Every quantum computer needs qubits, right, and gates. So we have our platform, our qubit register, and with a neutral atom quantum computer, we have a lot of back end hardware to create this qubit register and to reload this qubit register every tens of quantum operations. And then we have the hardware that provides our gates. So with a neutral atom quantum computer, that's lasers and microwaves, and lots of fun, optics, electro optical components, acoustic optical components. And then we have a control system, which really is the conductor, the timekeeper, which synchronizes all of these different parts. And with the neutral atom quantum computer, we take these atoms, we reload our register, perform operations, perform circuits. We can keep them around for a while, but eventually we do have to reload them again. So I guess that's to speak to how important the control system aspect is for our particular platform. But yeah, just qubits, gates, and then a control system. I would say those are the three main components.
Gotcha. And basically, after you get these neutral atoms out of the ground state, right, you need to cool them. And cooling is really a critical part to keep the qubits stable, right? And so these systems are typically cooled down to almost 0 Kelvin or absolute zero, basically. And this is performed with a special kind of a technique where also magnetic fields and lasers are involved, correct? Is that
Yeah, that's
okay?
correct. Yeah.
Okay. And can you help us a little bit to put this into perspective? Like, what is the time required for this atomic preparation, basically, until you actually can do the computation, right? So, and also, what is the kind of precision required? And how do you actually cool down atoms with a laser?
Yeah, it's kind of counterintuitive, isn't it? Because we do start with this chunk of strontium in our case in an oven. We have to heat the atoms to dissociate them in the solid.
Yeah.
So we sublimate this chunk of strontium. And so we have this hot strontium gas. And so from that point forward, the name of the game is to cool the gas
Mhm.
because, when atoms are like buzzing around, um, you can just imagine intuitively things can't be done as precisely. Like, how are you going to, capture this buzzing atom in one of your optical traps? So we do rely on a lot, all of the techniques that have been developed over the last 30, 40 years of laser cooling. Um, Quantum mechanics says that light, there's a wave particle duality of light. So you can think in one aspect of what we're doing is just bombarding the atoms with little photons, little balls of light, which have momentum. So, if an atom is like buzzing or flying this way and we're just kicking it with light, counter to its trajectory, we will eventually slow it down. And slowing it down, it goes hand in hand with cooling. Um, There are more sophisticated tricks we play where, like you said, we have magnetic fields to spatially couple a trapping, a location for trapping the atoms.
Mhm.
Because just shining a laser beam at these hot atoms doesn't really say anything about uh, space, right? I mean, there's no notion of coupling this cooling to a spatial location. And it does have to be done very precisely.
Yeah.
We're talking about hundreds of milliseconds, maybe a little bit longer of this sort of state preparation. And, trapping these atoms to a region at the end within, millimeters, micrometers. Because eventually we want to load them into an array of traps where the
Mhm.
traps are spaced by micrometers. Um, so it does have to be done exceptionally well, but these tricks and techniques have been pioneered in the field, and we're really just kind of following along in the footsteps of other academic groups. Yeah,
Yeah.
so
You just make it sound as it's so easy, but it's not. It's very very much state of the art what you're doing there, and well, impressive. Thanks you for explaining it so nicely. Now I understand it. So, like you said, like bombarding, basically, well, a laser is emitting photons, right? So you're sending these photons into the direction and basically slowing them down, which in the end, results in cooling. So nice explained. Thank you. Now it makes sense for me as well.
I should say at the end, we go from 400 degrees Celsius to 10 microkelvin. So
Right.
we're talking about 10 to the 7,
Yeah.
is that 10 to the 7? 10 to the 7, like reduction in this like temperature value. So I mean, thinking about it is quite impressive, that people have figured out how to do this.
And it's just in a few hundred milliseconds, you said, right?
Yeah, yeah.
Yeah. Wow. So little time to actually fix any errors and things like that. So yeah, precision is really really highly required also in terms of like the whole apparatus, right? It's like you got to make sure, like if you make little changes, you have to probably try out a few things and a lot of try and error, I guess, huh? Like.
Absolutely. And that's what I should say I've spent my PhD and postdoc studying is working on these platforms. And
Mhm.
the quantum engineers here, I mean, that's kind of our specialty is building these sorts of systems in this sort of way and doing it
Yeah.
uh, quickly, right, and well.
Yeah. And another really amazing part about the neutral atom approach was when I talked with your colleagues Denise Ruffner and Robin Cox in previous Qubites episodes. You can keep those much longer stable, right? She mentioned like 10 seconds or something like this, where you can keep the qubits in a stable state, which is very impressive. If you compare it to other approaches like with semiconductor or trapped ions and so on, it's just, what is it, nanoseconds, milliseconds or something like this, right? Where they can keep it stable. And so, well, you can do probably much more with 10 seconds of stable computation.
Yeah, our coherence time is tens of seconds long. And I mean, really, that's coming about because we're using neutral atoms. We're using the universe's like two-level system. We're not using a fabricated two-level system that, someone made.
Yeah.
It really is as perfect as it can get. There are subtleties there, but
Right.
yeah.
So, looking at your background, of course, you're not in a lab right now. Beautiful pictures there, actually, or like decoration. Um, yeah. So, can you tell us, since you're not in the lab, but what does a typical workday for you look like? And are you mostly actually working in the lab on actual hardware, or more on a computer and doing computations and simulations and figuring out certain things? Or and also, of course, what are the big challenges actually, from scaling to from a more, like, say, scientific physical system, like an apparatus in the end, into this commercial quantum computer? I think it's called Phoenix, right, for IDM computing.
Yes. Yeah, our first generation computer is Phoenix, which is in Berkeley, what I'm working on. And a typical day can be all of the above. I'm asked this question kind of, what do you do as a quantum engineer? And it always kind of stalls me a bit because I work on software, I work on hardware. Um, at the end of the day, I'm one of the people that see the physical system we have and are working to abstract it to the powerful quantum computer we know it can be. So it does require, work in automation and calibration, work on this process of cooling to make it better and more robust, working on our single qubit and two qubit gates to make the fidelities higher, increasing the atoms we're trapping. So you kind of do many different things, and I think that's why I enjoy this job so much, because it's never boring and you get to learn a bunch of different skills. But it's hard to quantify or describe. I do spend a lot of my time in lab, wrangling lasers, certainly. One of the challenges of making our system commercial, right, is to increase the uptime and remove kind of the human intervention that atomic physicists need to do. So that's always in mind. How can we make this more hands off? How can we do this better, or add machine learning, or have some sort of a calibration routine? And I think that we really got so I started in March of 2020. I had 3 days in the office before there was a shelter in place county order. And I was able to watch the other people, the more senior people at the company. We had few remote utilities. We still needed somebody to come into the lab and turn on the laser. But, by say May of that year, you could, trap atoms like from your bedroom if you wanted to. So, COVID has been challenging, but it's been really interesting to see the company's approach to it, and in ways I think forced us to really get a handle on the things that we need to have to be commercial and to build these machines well. So this was not the case in my postdoc lab. You definitely had to be there for every second of the experiment, right?
Gotcha. Well, that's pretty impressive. And one way to say is like COVID, of course, accelerated a lot of like remote work, but now it also accelerated like remote quantum computing labs kind of a thing, right? And well,
Yeah.
and it's the first step to get to the kind of QAAS, like quantum as a service, right? Where you can then bring this Phoenix quantum computer into some place, and then you can schedule a job remotely via whatever quantum as a service provider, and then it will run on the actual hardware, but you don't have to worry about it. You don't have to tune it. And that's perfectly, like you said, is like the goal is, of course, to make this happen, right? To that you don't need a lot of human intervention and like, things you need to tune and so on. Well, and COVID might have helped, well, a little bit with that. Well,
Yeah,
if we want to see some positive things, right? Um, well,
absolutely.
this is awesome. Thank you so much, Kayleigh, for all this explanation and the insights you shared today. Unfortunately, we're already a little bit at the end of the show, but we could talk for much longer, and I would love to learn much more. But again, thank you so much for joining us today and explaining it so well. This is very much appreciated.
Thank you for having me. This was fun.
Well, and thanks everyone for joining us for yet another episodes of Qubites, your bite-sized your bite-sized pieces of quantum computing. Well, watch our blog and follow our social media channels to hear all about the next episodes, and of course, visit our website to watch all the previous episodes from season 1 to 5, where we also had other colleagues from Kayleigh from Atom Computing, where we talked about a couple of other things. So you might want to see those as well. But anyhow, take care and see you soon. Bye bye.